concept you know it already, you should know it by now. All what we're going to do in this lecture mainly is to solve problems, different type of problems. Then we'll talk a little bit about friction. So this is that's what we're going to do in this lecture. If you remember, on Thursday we talked about pigs and pulleys, and we said that a pulley, a massless, frictionless pulley, all what it does is it changes the direction of the force, and nothing more than that. So if you have a force here that's T1, the force here is going to be same force T1. This is what does a pulley do. A spring, when you pull or push a spring, there will be a restoring force in the spring, a force that's trying to restore the spring back to its equilibrium position. So if you pull it or you push it, there will be a restoring force in the spring, and that restoring force will directly proportional to the displacement and in opposite direction, and we call that Hooke's law. This is Hooke's law. That constant here, K, that's the force constant, and that force constant has units. That's the units of that force constant, that's Newton per meter. And this is a simple example in here, that if you have a spring that has a force constant K, and we pull it to a distance from its equilibrium position equal to 1.5 meter, and if you know that the spring constant that's 14 Newton per meter, can you calculate the force, the restoring force on the spring? Again, you have a spring, this is the equilibrium position, then you pull it for a distance equal to 1.5 meters. You apply a force to do so, you apply a force to do so, but you do not know what is that force, what is the magnitude of that force. But you know that the spring constant, K, equal to 40 Newton per meter. So you need 40 Newton to pull it 1 meter. This is the meaning of the force constant. You need 40 Newton to pull it or push it for 1 meter. Now you pulled it for 1.5 meters. How much force should you apply? 60. So the answer is going to be 60. That's X. Oh, I'm sorry. X equal to 1? Yeah, I'm sorry. I thought that's X equal to 0. Equilibrium position is at X equal to 1. So you actually pulled it for 0.5 meter. So because the new position, it's 1.5 meters. So you pulled it only for 0.5 meter. So how much force should you apply? That's going to be 20 newtons. And if you know that the force is 20 newtons, then the restoring force, that's negative 20 newtons. So that's going to be the answer. That's negative 20 newtons. Now we're going to take actually a little bit advanced problem than with the problem that we have covered so far. We're going to assume that we have a plane, and tilted plane. This is the tilted plane, and you have an object on that plane, and the object is at rest. Or if is it moving? No, actually it's moving. It's moving with some acceleration A. So it's moving down with some acceleration A. And we need to find out what is that acceleration A. So what to do? We remember from last time that all what we have to start up with is to draw the free body diagram. So if you have a tilted plane like this, how would we draw the free body diagram? The trick here is we should draw the free body, the body as it is in the problem itself. So if it's tilted, then this is my body. This is the object. This is the object. Then we draw all the forces on it. So what are the forces on that object? The force, the gravitational force, that's mg. Correct? What else? Then from its name, the normal force is perpendicular to the surface. So from its name, this is the normal force, has to be perpendicular to that surface. So that's the normal force. Any other forces? Oh, forget that for now. Any other forces? Nagy, any other forces? Are you sure? Are you sure?
No.
So then you mean, so do we have any other forces?
Yeah.
Which is? What kind of force is that? Acceleration is due to the net forces on the object. It's not a force by itself. Acceleration, that's a result. Oh, there is no friction. That's good. Ali said there is a friction force, but actually you can read up there that the ramp is frictionless. So we have to ignore friction for now. How about this? How about the force from the object on the ground? How about no. This is the gravitational force. The gravitational force from the ground, from Earth to the object. So we can write it force from the object, on the object from the Earth. I'm here to talk about the force on Earth from the object. How about that force? Nagy.
On Earth on the object.
This is Earth on the object, and this is object on the Earth. We did not include that in the diagram. Here it is. It doesn't matter. Am I right? Am I right? Why not? Yes. Because the free body diagram, we only draw the forces on the object, not from the object. So we should not draw that one. So actually those are all the forces on the object. Yeah, but you're not really sure about your answer. So we draw only the forces on the object. Then, now this is the trick part. We have to choose a coordinate system. We used to choose a coordinate system before like this. This is our coordinate system. This is I, this is J. Now if you have your object is tilted, we choose the x-axis along the direction of the motion. We choose the x-axis along the direction of the motion, and the y-axis is perpendicular to that. So if the object is going to move like this, then this is my coordinate system. This is I, this is x-axis, and this is the y-axis. This simplifies things. That makes our life a little bit easier. Someone will say, can we do this? Can we tilt the coordinate system? Yes. If you remember, at the beginning of the course, we said that I'm going to choose that to be my x-axis and this is to be my y-axis, right? I can do this. This is my x, this is my y. I can do this. This is my x, this is my y. So I can do with my coordinate system the way I want. I can move it the way I want. As long as I have a coordinate system that has three axes that are perpendicular to each other, I'm free to do whatever I want. X, y, and z. Okay, guys? And I can even do this. If this is x, and this is y, and that's z. I can do this. This is my coordinate system. I can do that. This is my coordinate system. I can do whatever I want with my coordinate system. So to make my life easy in solving that problem, I'm going to choose the direction of the motion to be my x-axis, and any other, the y-axis will be perpendicular to that. So now someone said I have to resolve the forces. Then yes, now that was mg. So if I draw my coordinate system in here, just simply this is my coordinate system.
المشكلة MG not يعني still perpendicular to the ground لكن the X and Y axis is different.
Yeah.
يعني shouldn't the X axis be the ground?
No, the x-axis, that's the direction of the motion. Then all what we have to do now is to find out what is that angle. What is that angle? We know that the tilt angle here, that's theta. This is theta, and I claim this is also theta. Are they? Are they? If that's theta, and this is 90, of course. This is 90. This should be x, the angle axis should be 90 minus theta, right? So this is the same angle x. And this angle is 90, then this is the angle theta. So this angle is theta. Now, if I know that this angle is theta, mg, and if we know that this angle is theta, now can we resolve that mg? Then this is mg sine theta along the x-axis, and along the y-axis we have mg cosine theta. Now, and I can ignore that because I have resolved that into two components. Now I have all my forces aligned along my coordinate system. Next step, after drawing the free body diagram and putting all the forces on it and resolving the forces that need to be resolved. Yes, Shinawi.
If we find mg cosine theta, it should always equal to the normal force.
We'll find out. So that's our free body diagram. Second thing to do is to apply Newton's second law. Sum of the forces along the x-axis will equal to mass times the acceleration along the x-axis. Sum of the forces along the y-axis will equal to mass times the acceleration along the y-axis. What are the forces along the x-axis? That's only mg sine theta. Is it positive force or is it negative force? Why is it positive? Because it's along my x-axis, so that's positive force. Equals to mass times the acceleration along the x-axis. Guys, can you figure out what is the acceleration along the x-axis? Oh, sorry, g sine theta. That's the acceleration on the x-axis. Then that's easy. Now, can we apply Newton's second law along the y-axis? It's a normal force, positive normal force, because it's along the positive y-axis. Negative of mg cosine theta should equal to mass times acceleration along the y-axis. What is the acceleration along the y-axis? 0. Because the object does not leave that surface. It's always attached to the surface, and I know that surface now, that's my x-axis. So this is 0. Then, excuse me? 49.8. No, acceleration on the y is 0. Look at my y-axis. It's tilted now. This is my y-axis. This is my y-axis, the perpendicular to the surface. If the object leaves the surface, move up or down the surface, then there is an acceleration along the y-axis. But as long as it's moving along that surface all the time, then the acceleration along the y-axis is 0. I tilted my coordinate system. So from that equation, and the normal force will equal to mg cosine theta. Now we have also some information about the normal force. We got the acceleration and we got the normal force. So the key point here is you choose the direction of the motion along to be your x coordinate. The key point is you choose your x coordinate to be along the direction of the motion. And that's what we did. We have chosen our coordinate system. We draw our free body diagram. We put all the forces on the free body diagram. That's mg. Then we resolve that forces into two components. One along the x-axis, that's mg sine theta, and one along the y-axis, that's mg cosine theta. Then this is the direction of the motion. That's why I choose my x-axis to be along the direction of the motion. Then I apply Newton's second law along the x-axis. Before we do that, we draw the normal force from the surface on the object. Then, if we apply Newton's second law, so what we did is we have drawn our free body diagram, we put all the forces on, we determine our coordinate system in such a way that we have our x-axis in the direction of the motion, and we put all the forces on the free body diagram, that's mg, and we resolve mg into two components, mg sine theta and mg cosine theta along the y-axis. Then that's the normal force. Then we apply Newton's second laws. Newton's second law along the y-axis, x-axis equal to mg sine theta. That's the sum of the forces along the x-axis equal to mass times acceleration, and from that we can get the acceleration along the x-axis. Oh yes. Then we have along the y-axis, some of the forces along the y-axis, that's n upward, and mg cosine theta downward. That's why we said n positive n minus mg cosine theta equal to 0, and 0 because there is no acceleration along the y-axis. And if you look at those two equations, guys, those are only two equations. So you should have all the information but two unknowns in order to solve them. So I can give you theta, or I can actually put theta as one of the unknowns. Okay? So anyway, so now I'll take that into, if we have a problem, if we have two blocks, M1 and M2, we push them by a force F. And if we know the magnitude of the force F that's applied on M1, we need now to know what is the force on the block M2. This problem carries a clear misconception. That's why I choose that problem. So if I have two masses, and I'm going to push M1 with a force F. Now I'm asking you what will be the force on M2. What to do? We draw the free body diagram. Yes.
Are they always not in contact?
Yes, they are in contact all the time. Then we add the masses. But now you're not getting the forces on, you're getting the force on the system, but not on M2. So you're right. Then you can consider them as only one object, and in that case, you can, all what information you can, the information you can get is the acceleration of them and the forces on them. But if I ask you about the force on M2 by itself, you cannot get it. As I'm saying, it's F. It's going to be F. That's why I choose that problem. It carries a clear misconception. Let's solve it and see if it makes sense to us or not. Okay? So what I'm going to do is, I'm going to draw the free body diagram. And if we draw the free body diagram for each one of them, we have to take into consideration that the forces between them, the force from object number 2 on object number 1, sorry, for the force on object number 2 from object number 1, that's F21, and the force on object number 1 from object number 2, those two forces are equal in magnitude and opposite in direction. I'm going to consider only object number 2. Only object number 2, and I will draw the free body diagram for object number 2. Let me remind you, guys. I'll take you back one step. I'm looking only at that object, M2. What are the forces on M2? It's the force, the contact force between M2 and M1. That's F21, the force on object number 2 from object number 1. This is the only force acting on object number 2. Force 1 is directly acting on object number 1. It's not acting on object number 2. It touches object number 1, yes? Yes, that's why you have a force here. Otherwise you will not have it. And it makes it M2 moves on acceleration A. That's a result. So if we draw the free body diagram, put the forces acting on the object, then write down Newton's second law, sum of the forces acting on the object equal mass times acceleration. Look at that equation, we have two unknowns. Acceleration and force. We need to know one of them. If we need to know what F21, we have to find the acceleration. Now, Ali said, I can consider them as one object. True. And if I consider them as one object, I can get the acceleration because they are attached to each other all the time. They move with the same acceleration. So if they move with the same acceleration, from that information, I can assume that the two of them are one object. Look at the equation on the top. And apply Newton's second law in that, sum of the forces, which is F in that case. I'll go back one slide, which is F in that case. If you add all the forces on the two objects, those will cancel out even if you add them. So it's only F acting on the two objects. F will equal to mass times acceleration. M1 plus M2 times acceleration. And from that, we can find the acceleration. We can get the acceleration. Acceleration will equal to F divided by M1 plus M2. So we know the acceleration. If you plug in the value for the acceleration here, you can get the force on object number 2 from object number 1. So if we do this, we'll find that F21 equal to M2 times F divided by M1 plus M2. So it's not F actually. Someone said, Azam, you said F at the beginning. Now it's not F. It's actually part of F. And it makes sense. If the force F acting on M1 by itself on M2, and M2 is much lighter than M1 plus M2, that means that M2 has to move with an acceleration more than M1 and M2, and that does not happen. Right? It has to be part of the force F. And of course, F21, it's going to be only part, fraction of F. So that's it. Now, another problem. A little bit, not that complicated, but a little bit harder problem. So I'm going to hang that mass M with two ropes. I'm going to hang that mass M with two ropes, and I need to find out what is the tension in each rope. Each rope. So what to do? I'll draw the free body diagram. I'll draw the free body diagram for the object first, for the object. That's mg, and that's the tension T. Ft. Then I'll draw the free body diagram for that point. T, tension T, is pulling that point down, and T1 is pulling it in that direction, and T2 is pulling in that direction. That angle is theta, and that angle is also theta, as given by the problem itself. I'm going to divide the problem into two problems. Now, here we can find that T, sum of the forces, will equal to mass times the acceleration. T minus mg will equal to 0. Why 0? Because it's not moving, nothing is moving. And then T equal to mg. Now we know what's T. In here, what to do? I have to resolve T1 and T2. So this is going to be my coordinate system. I and J. T1, it's going to be resolved into two components. One along the x-axis, that's T1 cosine theta. And one that's along the y-axis, that's T1 sine theta. T2.
The y-axis for T1 and T2 is the same?
What do you mean? Yes, it is the same. Then T2 is going to be resolved into two components as well. That's T2 cosine theta along the negative x-axis and T2 sine theta along the positive y-axis.
There's something I don't understand.
Excuse me?
There's something like, why isn't it T2 cosine theta divided by 2? T1 cosine theta divided by 2 with T equals,
What is 2?
yani, why isn't the x and y component
Mhm.
and divided by 2? Because
Sometimes not 45 degrees to divide by 2.
Why don't we divide them by 2?
yeah, because tension is less because there's two ropes. And adding the two tension.
I don't know what's T1. You're saying now that T1 is equal to T over 2?
I think so. Yes.
I don't know this. We don't know this. Yes, it's going to be T over 2 if the two angles are equal, but we don't know that now. We know it after we solve that problem. I assume that.
Theta and theta, they have to be.
Making an angle theta. That's why I assume that this T1 and T2, I will assume that they are not equal, and we'll find out. If they are equal, it will show.
If they're equal, then they're equal.
How do you know that? Common sense, right? It's common sense. And sometimes our common sense is not really true. So I have to make sure that my common sense makes sense. And that's what I'm going to do. If you give me a minute, we'll see. You're right, but I have to prove it. Ali.
Isn't it might be the ropes of different materials, so the tension, even if the angle is the same,
We assume that the ropes are massless.
okay, but the tension might be different even if the angle is.
If the ropes are different, but if we assume that the ropes are massless, does not have any mass, then they almost the same. They are the same. Okay? Now, sum of the forces on the x-axis equal to mass times acceleration and equals to 0 because there is no motion. And from that equation, what are the forces along the x-axis? Nada. No, x-axis. T1 cosine theta along the positive x-axis minus T2 cosine same angle theta equals to 0. That means that T1 cosine theta equals to T2 cosine theta. Cosine theta cancel out, then you get T1 equal to T2. That's what you were saying, and we have proven that. Then she now said that T1 and T2 will equal to T over 2. We'll find out. Now, in that part, sum of the forces along the y-axis will equal to 0. Since we don't have any motion along the y-axis, that means that T1 sine theta plus T2 sine theta minus T equal to 0. Okay, can I do this? T1 is equal to T2, so this is T1. Then you have 2 T1 sine theta equal to T equals to mg. Then you have T1 equal to mg, which is T divided by 2 sine theta. If theta is 0, sine 0 is 0. So what will be the tension? It's infinity. It's going to be huge tension. And if theta is 90, then what will be T1? T over 2. Okay, but it's not t over 2 unless the angle is not actually is something else. Yeah. So she now was saying that the t1 would equal to t divided by 2. And actually, what I see now that t1 equal to t, the mg, divided by 2 sine theta. So t1 is a function of sine theta. t1 is going to change if you change sine of the angle theta. So if you choose angle theta to be 0, so the ropes are like this and they attach to somewhere in infinity, the tension is going to be huge. It's going to be infinity. And if the two ropes are like this, then the tension will be, in each one of them will be T over 2. Okay, Shinawi? So guys, that's the solution. From the sum of the force along the x-axis, you get T1 equal to T2. From sum of the force along the y-axis, you can get some information, more information about T1 and T2. You can actually get a numerical value for T1 and T2 if you know the mass, the G, and the angle theta. I'm going to skip that. Friction. Friction. What does friction do? It's always oppose the relative motion of two objects. It's always oppose the relative motion of two objects. My hand. I'm going to do this. I'm going to rub my hand against each other. So I'm going to move the right hand and I will fix the other one. I'll do this. What is the direction of the friction force on that my right hand? Okay. What is the friction of? What is the direction of the friction force on my left hand? Relative motion. Actually, my right hand sees my left hand as if it's moving along what direction? That direction. So the friction force on my left hand is going to be along, always opposite to the direction of the relative motion. Always opposite to the direction of the relative motion. So if my left hand appears as if it's moving along that direction, then the friction force is going to be along that direction on my left hand. Again, let's do that one more time. Okay, guys? So I'm going to move my right hand in that direction. What is the direction of the frictional force on my right hand? It's towards me. It's opposite to the direction of the motion. Now, my left hand. What is the direction of the frictional force on my left hand? This, my left hand, it will appear as if it's moving along my direction relative to my right hand. So if this is the direction of the motion, then the direction of the frictional force is in the opposite direction. So now if I move on the floor, if I move on the floor, what is the direction of the frictional force on my feet? I'll do it again. On my feet, direction of, what is the direction of the force, of the frictional force on the floor? Along my motion, yes, correct. Which is opposite to the direction as if the floor is moving and I'm constant. I'm not moving now. Okay? So this is the frictional force. Why do we have frictional force? Why do we have a friction force? Because if we look at the microscopic scale, at the very small scale, on any objects, there is nothing called a smooth surface. Sorry. If you put your finger like this on the desk, it feels smooth to me, right? But if you bring a needle, very sharp needle, and you put it on the desk, then the needle is going to do this. The desk is not going to be as smooth as you measured by your finger. So that's something that's relative. Nothing called smooth. It's relative how you measure it. So if you look at the microscopic scale at any two surfaces, they will look like this. And the interaction between the two surfaces causes friction. And that friction, it's preventing somehow, it's resisting somehow the motion, and at the same time, it produces heat. Rub your hand, you feel the heat. It produces heat. So this is what happens. So we have two kinds of friction. We have a static friction. That's why my mobile is not actually slipping along that surface, even though it's tilted. We have friction that's preventing it from slipping till a specific angle, then to start slip. Once it moves, the friction get transformed from static friction to a kinetic friction. One of them is larger than the other one. The frictional force in one of them is more than the other one. And we'll find out which one is more. If you look at that picture, you can guess what happens. If it's static, that's what happens. They don't move, the two objects. If it's kinetic, this is what happens. The top jump on the top of the two surfaces, the hells on the two surfaces, and that's why the motion happens. Then you have a kinetic friction. So we have actually two kinds of friction, static friction and kinetic friction. Usually the frictional force is given by the frictional force. This is very important. Frictional force equal to coefficient of friction, a constant, times the normal force. The frictional force equal to the coefficient of friction times the normal force. That coefficient of friction, it can be static if there is no motion, and it can be kinetic frictional force if there is motion. Usually the mu k is less than mu s. The mu k, the coefficient of friction, is less than the coefficient of kinetic friction is less than the coefficient of static friction. Before you ask, guys, look at that equation. What is the units for that coefficient of friction? It's unitless. Why? Because actually if you rearrange the equation, you'll find out that mu, regardless of its type, if it's kinetic or static, equal to the frictional force divided by the normal force. Those are ratio that's a unitless. Sharif.
Doctor, we know that the friction force at the kinetic level is opposing the direction of motion. At the static
It's the same. If it's to move, if that object is to move, in what direction will it move? That way.
So it opposes the net force, the magnitude. So like
It opposes the direction of the motion. So you have to find out if this is going to move. Well, the common sense tells us this will move along that direction. So the frictional force is along that direction. That's why it's preventing it from moving. If that's a frictionless surface, it will move. It will move by the effect of gravity, a component of it, a component of the gravitational force, right? If this is frictionless, so if this is ice, then you put that on the ice, then it's going to move in that direction. Okay? Oh, like that. Then if you look at the surface of that surface under the microscope and that surface under the microscope, you will see them as smooth as you see them now. They are rough surfaces, and the hell in one of them gets into the valley on the other one, and that's what happens. Yes, under the microscope. Yes, Now, of course, it depends on how you measure it. So if you measure by your finger, it's smooth. But if you bring a needle that's very, very sharp, very, very sharp, and you put it on a spring, a needle that's very, very sharp, and you put it on a spring and you try to move it, you'll find the spring is doing this all the time. Because the needle is going to go into the grooves between in here, and it's going to move up and down all the time. So it's not surfaced as measured by the needle. That's relative. Okay, but so on the microscopic scale, that's what causes friction. The roughness of the surface. Yes.
The friction force, does it change?
Yes, that's a very good question in here. Does it change? Yes, it depends on the two types of material that we're going to use, my hand and the chair. Not only that.
No, I mean, if these two types of material are constant, does it change?
No.
No. Then
Coefficient of friction, this is tabulated between, let's say, wood and iron.
So it's also,
It's constant.
so how come, constant for these two materials, so how come static is more than, the coefficient of static is more than kinetic?
Because that's what happened. Because if you look again at the microscopic picture of that, that's what happens. When it's static, this is what happens between the two materials. So the force is huge between them. Look at the surface area of interaction. Look at the surface area of the interaction between them. There's a huge surface area, right? Look at this. When they move, they don't have that time to interact with each other that way. They move, the top of the hull moves on the top of the hull of the two surfaces. The two hulls on the two surfaces, they move on top of each other, and that's what happens. Can we bring that friction book next time? Okay? That's why the kinetic friction. Now look at the surface area. It's much less than this. Surface area of interaction between the two objects, between the two surfaces. Okay? And the friction force actually depends on the area. The more the area, the more the interaction between the two surfaces, the more the friction force. So when you go, you buy tires for your car, the wider the tires, the better. We need friction force to move. Without friction force, we wouldn't be able to move. So friction force can be useful sometimes for us when you try to move on ice. You will not be able to move on ice because there is no friction. Okay? And sometimes it's harmful. The cylinders in your car, the piston and the cylinder in your car, the engine goes into you have a piston that goes into the cylinder, and there's friction between those all the time, and by time those there will be a wear in the cylinder, and you have to replace it. Okay, by a wider one.
A wider tire is better because more surface area.
More surface area, and the more the surface area, the more the friction. And I will show you a demonstration on that next time. Okay? And I have bought some I have bought two websites for something that measures friction sometimes. That's a new device. It's called the atomic force microscope. Look at it. It's very neat. Friction force leads to heat. Other forces like gravity, they do not lead to heat. We can actually divide forces now. If you remember, we divided forces into contact and non-contact forces. Now I'm going to divide them into conservative, and we'll talk about that in chapter 7, and dissipative. Conservative, they do not cause heat. Dissipative, they cause heat. And external forces, that's us. So now if I push Ali, there is an external force, that's my hand pushing on Ali. I call that external force. The friction force between Ali and the chair, that causes heat. If Ali moves on the chair, he will feel the heat. But gravity, if you drop something, there will be no heat from this. We call gravity, electric and spring forces, those are conservative forces. And keep that word in your mind till chapter 7. We'll talk about why do we call it conservative forces and why we call friction non-conservative forces. Now, friction. I'm going to include friction. We have studied that problem before without friction. We have been pushing that object with a force F along that direction, and we have assumed before that that surface is frictionless. Now we're going to include friction. And I need to find out what will be that friction force. What will be the friction force? What is the magnitude of the friction force? So if we draw the free body diagram, you get mg down, gravitational force down, normal force from the surface on the object up, that's the normal force. The force of F that we push the object with is to the right. Friction force is opposite to the direction of the motion, it's to the left, and it's between those two surfaces. And now if we apply Newton's second law along the x-axis, you get F minus the friction force equals to mass times acceleration. That's one. If we apply Newton's second law along the y-axis, you get N minus mg equals to 0. That means that N equals to mg. And we know that the friction force equal to mu, coefficient of friction, times the normal force. So if we know that N equal to mg, then the frictional force will equal to mu times mg. Okay guys? Mu times mg. And which mu? Kinetics, because there is motion. Thank you. So I'm going to stop here, guys, because we don't have time actually.